Hello and welcome back to the channel. In today's video I'm overclocking the AMD Radeon 760M integrated in the Ryzen 5 8600G Hawkpoint APU, and we're overclocking it to 3150 MHz using the GIGABYTE B650E Aorus Elite AX Ice motherboard and custom loop water cooling. Now, this is the second integrated graphics of Hawkpoint that I've overclocked on this channel. I've previously overclocked the 780M integrated in the 8700G. And again, we're going to focus on fine-tuning the graphics performance with paying special attention to memory timing tuning, because that showed to have a large impact on performance in our previous integrated graphics overclocking guide. Anyway, let's get started. The Radeon 760M is not a new product, as it was also available in the 2023 Phoenix mobile lineup. For example, the Ryzen 5 7640HS already featured these integrated graphics. The Radeon 760M is only available on the desktop with the Ryzen 5 8600G APU. A critical difference between the Ryzen 7000 CPUs and the Ryzen 8000G APUs is that the former is a multi-chiplet based design and the latter features a single monolithic die. What's also exciting about the Ryzen 8000G processors is that it's the first AMD desktop product manufactured using the TSMC N4 process. Hawkpoint is the successor to AMD Cezanne, which was launched in 2021. I already overclocked one of the Hawkpoint APUs on this channel, the 8700G and its integrated graphics in SkatterBencher's 69 and 70. AMD finally brought the RDNA 3.0 architecture to the desktop APUs, as the integrated graphics for the Ryzen 7000 processors was still the RDNA 2.0 architecture. Compared to RDNA 2, AMD claims a 54% generational performance uplift. RDNA 3 also features the second generation Ray accelerator and a bunch of other architectural improvements. The Radeon 760M has 4 workgroup processors or WGPs with 8 compute units or CUs and 8 Ray accelerators. The maximum GPU frequency is 2.8 GHz, the TDP is 65 Watt and the TJ Max is 95 degrees Celsius. In this video, we will cover 5 different overclocking strategies. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, of course, we need to check the performance at default settings. The default Precision Boost 2 parameters for the Radeon 760M are as follows. Here's the benchmark performance at stock. When running the 3DMark Speedway stability test, the average GPU effective clock is 2816 MHz with 1.026 volts. The GPU memory clock is 2400 MHz. The average GPU ASIC power is 52.5 watts. When running the OCCT 3D standard stress test, the average GPU effective clock is 2733 MHz with 1.01 volts. The GPU memory clock is 2400 MHz. The average GPU ASIC power is 87 watts. In our first overclocking strategy, we take advantage of enabling Precision Boost Overdrive and AMD EXPO. Precision Boost Overdrive 2 is AMD's overclockers toolkit, which provides end users like you and I with the necessary tools to fine-tune the Precision Boost boosting algorithm. It's primarily used to overclock the CPU cores, but it also has some tools to overclock the integrated graphics. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the overclocking knobs from Zen Plus, PPT, TDC, and EDC, and Zen 2, Boost Override and Scaler, Precision Boost Overdrive 2 also introduced Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and to a lesser extent the TDC and EDC will help unleash the frequency in extreme workloads previously limited by any of these limiters. Unlocking the power limits can really make this little APU scream, especially in perhaps unrealistic workloads where we load the CPU cores and the graphics at the same time. One way to check that is by using the OCCT stress test tool. Here you can see the APU run at over 200 watts. That's 3 times the rated TDP. EXPO stands for AMD Extended Profiles for Overclocking. It's an AMD technology that lets memory vendors such as G.Skill program higher performance settings onto their memory sticks to enable ubiquitous overclocking on AMD DDR5 platforms. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting, so it saves you from a lot of manual configuration. As we'll see later in the video, unlocking memory performance is critical to improving APU graphics performance. Upon entering the BIOS, in easy mode, set XMP EXPO profile to EXPO 1. Switch to advanced mode and stay in the tweaker menu. Enter the advanced CPU settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to enabled, then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Unlocking the power limits and enabling higher memory performance significantly impacts the integrated graphics performance. The geo-mean performance improvement is plus 12.99%, and we get a maximum improvement of plus 22.86% in Tomb Raider. When running the 3DMark Speedway stability test, the average GPU effective clock is 2824 MHz with 1.027 volts. The GPU memory clock is 3200 MHz. The average GPU ASIC power is 62.2 watts. When running the OCCT 3D standard stress test, the average GPU effective clock is 2835 MHz with 1.05 volts. The GPU memory clock is 3200 MHz. The average GPU ASIC power is 98.1 watts. In our second overclocking strategy, we leverage some of the PBO tools to unlock more graphics performance. Fused Maximum Frequency, or FMAX, is a precision boost infrastructure limiter that determines the maximum allowed graphics frequency. GPU Boost Clock Override, or GPU FMAX Override, is one of the overclocking tools available in the PBO2 toolkit. It allows the user to override the arbitrary clock frequency limit up to plus 200 MHz in steps of 25 MHz. It's important to note that this GPU Boost Clock Override only extends the upper ceiling of the graphics frequency. It doesn't operate as an offset. So the Precision Boost algorithm still determines what is the right graphics frequency for a certain workload. When we increase the GPU FMAX boost limit by 200 MHz, the new GPU Boost FMAX is 3000 MHz. A last quick setting I want to discuss before moving on to the BIOS settings is the high bandwidth support memory option. I used this in previous guides and it seems to provide additional performance benefits, but GIGABYTE is pretty tight-lipped on what it does exactly. Enabling the setting may cause instability, so it's up to you to see if your memory is stable when enabled. Upon entering the BIOS, in easy mode, set XMP EXPO profile to EXPO 1. Enable XMP EXPO high bandwidth support. Switch to advanced mode. Change to the settings menu. Enter the AMD overclocking submenu. Click Accept. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Set GPU Boost Clock Override to Enabled. Set Max GPU Boost Clock Override to 200 MHz. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. With only a slightly higher frequency of 200 MHz, we didn't expect much of a performance improvement. However, nothing is further from the truth and we get a pretty substantial performance uplift. Compared to the previous OC strategy, the geomean performance improved by 8 percentage points, and we get the highest performance improvement over stock of plus 29.41% in returnal. When running the 3DMark Speedway stability test, the average GPU effective clock is 3003 MHz with 1.186 volts. The GPU memory clock is 3200 MHz. The average GPU ASIC power is 79.2 watts. When running the OCCT 3D standard stress test, the average GPU effective clock is 3014 MHz with 1.2 volts. The GPU memory clock is 3200 MHz, and the average GPU ASIC power is 121.1 watts. In the third overclocking strategy, we're pursuing a manual overclock, and my goal is to adjust and fine-tune all the frequencies that can affect the graphics performance, which includes obviously the graphics clock, but also the fabric clock, the memory clock, and the memory controller clock. But before we go ahead and adjust those frequencies, let's first have a look at the AMD Hawkpoint clocking and voltage topology, which will give us a better understanding of where the tuning opportunities lie. The clocking of Hawkpoint APUs is similar to other Zen 4 desktop processors. The standard Hawkpoint platform has a 48 MHz crystal input to the integrated CGPLL clock generator. The CGPLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. As a whole, this provides a CPU clock frequency granularity of 25 MHz. Each CCX has its own PLL, with the cores within that CCX running at the same frequency. This isn't particularly relevant since there's only one CCX, featuring 6 Zen 4 cores. The SoC PLLs include a wide range of PLLs present on the die. AMD's Hawkpoint voltage topology is similar to that of the previous Ryzen processors. There are 4 primary power supplies from the motherboard VRM to the processor. The VDD-CR voltage rail provides the external power for 3 internal voltage regulators. The VDD-CR CPU provides the voltage for the CPU cores within the CCX. The voltage rail can work in either regular or bypass mode, but it's always in bypass mode on Hawkpoint. That means the voltage of the cores is always equal to the VDD-CR external voltage. The end user can change this voltage in the BIOS. VDD-CR VDDM provides the voltage for the L2, L3, and if present, 3D V-cache on a CCX. This voltage rail is always internally regulated from the VDD-CR external voltage rail, and we cannot adjust this voltage. VDD-CR GFX provides the voltage for the integrated graphics. In the past, this voltage would be provided by the VDD-CR SoC voltage rail. It's likely due to the high current requirements of the powerful integrated graphics that using the beefier VDD-CR voltage plane is safer. This voltage is limited to 1.25 volt under ambient conditions and requires LN2 mode for a higher voltage range. The VDD-CR SoC voltage rail provides the external power for multiple internal regulators on the SoC for the various IP blocks, which includes the memory controller, the SMU, the PSP, and so on. Again, we can manually set the VDD-CR SoC voltage to 1.3 volt under ambient conditions, but if we want higher voltages, we need LN2 mode. Manual overclocking of the Radeon 760M integrated graphics is pretty straightforward. It's a process of trial and error. So you set a frequency and you check whether it passes your stress test. So for example, I tried setting the F clock to 2500 MHz and it failed to pass my stress test. So I stuck with 2467 MHz instead. Overclocking the memory and the memory controller are tied together. In my case, I could run them in sync up to DDR5 6400. For higher memory frequencies, I had to reduce the U clock to half the speed of the M clock. So for this overclock, I stuck with DDR5 6400. Overclocking the integrated graphics themselves was a little bit of a mixed bag. In theory, we should have more overclocking headroom than the Radeon 780M because, well, we start at a lower operating frequency and the manufacturing process and the graphics architecture are identical, and also because we have less compute units. So we have less of a thermal constraint when it comes to pushing up the voltage and the frequency. The overclocking results were not just similar to the Radeon 780M, they were identical. 3150 MHz in our worst case stress test. I could further increase the frequency to 3250 MHz in lighter workloads like 3D Mark Speedway. Upon entering the BIOS, in easy mode, set XMP EXPO profile to EXPO 1. Enable XMP EXPO high bandwidth support. Switch to advanced mode. Go to the settings menu. Enter the AMD overclocking submenu. Click accept. Enter the manual iGPU overclocking submenu. Set GFX clock frequency to 3150. Set GFX voltage to 1250. Leave the manual iGPU overclocking submenu. Enter the DDR and Infinity Fabric frequency timings submenu. Enter the Infinity Fabric frequency and dividers submenu. Set Infinity Fabric frequency and dividers to 2467 MHz. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric frequency and dividers submenu. Leave the DDR and Infinity Fabric frequency timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Leave the Precision Boost Overdrive submenu. Enter the SoC Uncore OC mode submenu. Set SoC Uncore OC mode to Enabled. Leave the SoC Uncore OC mode submenu. Enter the SoC Voltage submenu. Set SoC Voltage to 1300. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Despite the tiny improvement in GPU core frequency, we still get a little bit of a performance boost thanks to the improvements in the memory subsystem performance. Compared to the previous overclocking strategy, the geomean performance improved by 4.5 percentage points. We also get the highest performance improvement over stock of plus 35.29% in returnal. When running the 3D Mark Speedway stability test, the average GPU effective clock is 3162 MHz with 1.25 volts. The GPU memory clock is 3200 MHz. The average GPU ASIC power is 82.2 watts. When running the OCCT 3D standard stress test, the average GPU effective clock is 3163 MHz with 1.2 volts. The GPU memory clock is 3200 MHz. The average GPU ASIC power is 124.2 watts. In the fourth overclocking strategy, we try to further push up the IGP performance by also overclocking the CPU cores and, for the first time, digging into the memory timings. I rely on the information from SkatterBencher number 72 when it comes to overclocking the APU cores of the Ryzen 5 8600G. I won't go into detail here why we apply certain settings, because you can just watch that video to learn more about how to overclock the cores of this APU. I really wanted to include memory timing tuning in this overclocking guide because of the huge performance improvements we saw in SkatterBencher number 70 when we overclocked the Radeon 780M integrated graphics. There were three things I wanted to achieve. 1. Double check if optimizing the memory timings indeed has such a huge impact on performance, or if my previous results were a fluke. 2. Try to optimize the timings of my DDR5 6400 EXPO kit and see the performance improvement. 3. Find a more stable configuration for the fast DDR5 7800 XMP kit so I don't have the weird green flashes during 3D loads. In this OC strategy, I'm focused on the EXPO kit, while the XMP kit will be used in the next OC strategy. Now, I am far from a memory performance tuning expert. In fact, I'm what Buildzoid would refer to as a normie when it comes to memory overclocking. Now, Buildzoid is an absolute legend when it comes to memory overclocking. And the great thing about Buildzoid is that he shares a lot of his knowledge on his own YouTube channel called Actually Hardcore Overclocking. There you can learn about memory overclocking for a wide variety of platforms. What's even better is that he shared a document titled Easy Memory Timings for Hynix DDR5 with Ryzen 7000. And that's my starting point for memory timing tuning. For the most part, these optimized memory timings work just fine. The system passes the OCCT memory stress test workload without issues, except I still get green flashes during a 3D workload. To make a long story of testing every memory timing to find the culprit short, turns out the TRAS timing has to be adjusted to avoid the green flashes. When I change the TRAS from 30 to 34, the green flashes no longer appear. As a side note, these green flashes are a very strange phenomenon. Let's take this configuration where I no longer have the green flashes. So when I change the memory controller frequency to half that of the system memory frequency, so half of what we're running in this stable configuration, I get the green flashes again, and it's much worse. So it's very counterintuitive. I would reduce the frequency, thereby, I assume, improving stability, yet there's more green flashes than ever. Anyway, that's something to figure out in the next SkatterBencher guide when I do another Hawkpoint integrated graphics overclocking journey. Upon entering the BIOS, in easy mode, set XMP EXPO profile to EXPO 1. Enable XMP EXPO high bandwidth support. Switch to advanced mode. Stay in the tweaker menu. Enter the advanced memory settings submenu. Enter the memory subtimings submenu. For the standard timing control timings, set CAS latency, TRCD and TRP according to the EXPO specification. Set TRAS to 34. For the advanced timing control timings, set Buildzoid's Easy Hynix memory timings for Ryzen 7000. Leave the memory subtimings submenu. Leave the advanced memory settings submenu. Change to the settings menu. Enter the AMD overclocking submenu. Click accept. Enter the manual iGPU overclocking submenu. Set GFX clock frequency to 3150. Set GFX voltage to 1250. Leave the manual iGPU overclocking submenu. Enter the DDR and Infinity Fabric frequency timings submenu. Enter the Infinity Fabric frequency and dividers submenu. Set Infinity Fabric frequency and dividers to 2467 MHz. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric frequency and dividers submenu. Leave the DDR and Infinity Fabric frequency timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Leave the Precision Boost Overdrive submenu. Enter the SoC Encore OC mode submenu. Set SoC Encore OC mode to Enabled. Leave the SoC Encore OC mode submenu. Enter the SoC voltage submenu. Set SoC voltage to 1300, then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. We can largely ignore the benefit of CPU overclocking as, just like with the Radeon 780M, it has minimal impact on the graphics performance. However, tuning the memory timings is pretty impactful. It provides us with a 4 percentage point geomean performance improvement over the previous OC strategy. That's a similar improvement like we got from optimizing the operating frequencies of the graphics, fabric, and memory subsystem. We get the highest performance improvement over stock of plus 41.18% in Returnal. When running the 3D Mark Speedway stability test, the average GPU effective clock is 3155 MHz with 1.25 volts. The GPU memory clock is 3200 MHz. The average GPU ASIC power is 79.4 watts. When running the OCCT 3D standard stress test, The average GPU effective clock is 3150 MHz with 1.25 volts. The GPU memory clock is 3200 MHz. The average GPU ASIC power is 125.4 watts. In the fifth and final overclocking strategy, I once again tried to achieve the maximum performance uplift by swapping out the memory sticks, just like I did in SkatterBencher number 70. Now, rather than just showing you kind of an unstable configuration as I did in SkatterBencher number 70, in this overclocking strategy, I wanted to figure out what is the root cause of the instability and those green flashes, fix them, and have what I could consider a stable configuration. That's easier said than done though. Let me explain. As the tuning starting point, I took the memory subtimings that we got in SkatterBencher number 70, applied them to the system, and everything worked as expected, including those annoying green flashes. Then I took what I learned from OC strategy number 4, increase TRAS to get rid of the green flashes. In addition, I also adjusted the primary memory timings, TCL, TRCD, and TRP, according to the XMP kit specification. That worked just fine to eliminate the green flashes, so it's good enough for this OC strategy. Do note though that it didn't pass my memory stability test, but I ran out of time to figure out more stable settings. I did have a closer look at the memory performance scaling. In my previous Hawkpoint IGP overclocking guide, I mentioned that the memory timings are crucial for graphics performance. Based on further testing data, you can clearly see why. We can match the 3D performance of an untuned XMP 7800 kit with a well-tuned EXPO 6400 kit. Furthermore, it is more clear now what's driving the performance gains, as the memory copy bandwidth correlates the strongest with 3D performance. Anyway, now that we know how to tune this XMP memory kit, let's jump into the BIOS. Upon entering the BIOS, in easy mode, set XMP EXPO profile to XMP1. Enable the XMP EXPO high bandwidth support. Switch to advanced mode. Stay in the tweaker menu. Enter the advanced memory settings submenu. Enter the memory subtimings submenu. For the standard timing control timings, set CAS latency, TRCD and TRP according to the XMP specification. Set TRAS to 46. For the advanced timing control timings, set the optimized memory timings from SkatterBencher number 70, OC strategy number 5. Leave the memory subtimings submenu. Leave the advanced memory settings submenu. Change to the settings menu. Enter the AMD overclocking submenu. Click accept. Enter the manual iGPU overclocking submenu. Set GFX clock frequency to 3150. Set GFX voltage to 1250. Leave the manual iGPU overclocking submenu. Enter the DDR and Infinity Fabric frequency timings submenu. Enter the Infinity Fabric frequency and dividers submenu. Set Infinity Fabric frequency and dividers to 2467 MHz. Set uClock div1 mode to uClock equals memclock divided by 2. Leave the Infinity Fabric frequency and dividers submenu. Leave the DDR and Infinity Fabric frequency timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to Advanced. Set PBO limits to Motherboard. Leave the Precision Boost Overdrive submenu. Enter the SoC Uncore OC mode submenu. Set SoC Uncore OC mode to Enabled. Leave the SoC Uncore OC mode submenu. Enter the SoC voltage submenu. Set SoC voltage to 1300. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. The performance improvement from switching to a higher performance memory kit is once again very impressive. Compared to the previous OC strategy, the geomean performance improved by 10 percentage points. That's a bigger performance improvement than what we got from switching from a tuned PBO to a fully manually tuned configuration with DDR5 6400. We get the highest performance improvement over stock of plus 58.66% in Furmark 1080p. When running the 3DMark Speedway stability test, the average GPU effective clock is 3158 MHz with 1.25 volts. The GPU memory clock is 3900 MHz, and the average GPU ASIC power is 92.5 watts. When running the OCCT 3D standard stress test, the average GPU effective clock is 3155 MHz with 1.25 volts. The GPU memory clock is 3900 MHz. The average GPU ASIC power is 126.4 watts. Alright, let's wrap this up. I was as excited about overclocking the Radeon 760M as I was when I first overclocked the Hawkpoint integrated graphics in SkatterBencher number 70. It's really cool to see the graphics performance scale so well with memory fine-tuning, and it makes it a very different type of guide than what I usually do for CPU overclocking. The overclocking experience of the 760M is nearly identical to that of the 780M, which means that the graphics clock frequency doesn't really have that much headroom. We achieved 3.15 GHz for both parts, but you get a lot of extra performance by unlocking the power limits and especially from the memory fine-tuning. So that's a lot of fun. There's still some things that I want to uncover about Hawkpoint. Of course, I still want to figure out what's going on with those green flashes. So maybe I'll look at that in a future guide. And I also, at some point, want to check out the IPU performance. Anyway, that's all for this guide. I want to thank you for watching. And of course, I want to thank the patrons for their support. If you have any questions or comments, drop them in the comment section below. I'll also put up a written version of this video up on my blog if you want to read through the settings or check out my benchmark results. And that's it. See you next time.